The question states how many of these molecules are polar. For it to be a polar molecule, bond dipoles don't cancel, all domains aren't the same, and there's going to be a net molecular dipole.
Therefore, to find out if the molecules are polar, we're going to draw the Lewis structures, find partial charges in bond dipoles, and find the net molecular dipole.
So if we view the first molecule, which is going to be sulfur trioxide, we know that sulfur has 6 valence electrons and oxygen has 6 valence electrons each, and there's 3 of them. So you're going to get a total of 24 valence electrons. So when we put them on the Lewis structure, we try to fill up the octets on the outside first. So we put 6 valence electrons plus the bond on each oxygen, which makes 24. But the octet rule states we need 8 valence electrons on all of the atoms, and sulfur doesn't have 8. It only has 6. To fix this, we're going to put a double bond on the oxygen and remove 2 of the non-bonding electrons. And we can do that in 3 different ways. And because of this, it's a resonance molecule. The resonance structure is actually going to have a shared bond between all 3. So there's going to be 1 and 1/3 bonds between the S and the oxygens. Now the molecular geometry is going to be trigonal planar because there's 3 domains and no non-binding electrons. And for the dipole bonds, we need to look at electronegativity. The electronegativity of sulfur is 2.5 and the electronegativity of oxygen is 3.5. The electron is going to move towards the most electronegative one. So therefore, this one is going to have a partial negative charge. All oxygens are going to have partial negative charges, and the sulfur is going to have a partial positive charge. And since all 3 domains are the same, it makes it nonpolar. The dipoles are going to cancel, and there's going to be no net dipole. The second molecule is oxygen difluoride. It's going to have a Lewis structure that looks like this. Fluoride has an electronegativity of 4.0, and oxygen has an electronegativity of 3.5. The electron is going to move towards the most electronegative atom, so the bond dipole is going to go outwards towards fluoride, giving a partial negative charge on both fluorides, and the oxygen will have a partial positive charge since it's losing an electron. There's 4 domains, 1, 2, 3, 4, making it a tetrahedral domain geometry. However, there are 2 bonds and 2 sets of non-bonding electrons, making it a bent molecular geometry, which is going to look like this. The bond dipoles will cancel, but there are also 2 sets of non-bonding electrons, which cause net dipole movement that looks like this. Since all the domains are not the same, because there's a net dipole moment, that makes the molecule polar. Our next molecule, beryllium chloride, which is going to have a Lewis structure that looks like this. There are 16 valence electrons. So you're going to fill up the chloride, the outside atoms, to make the octet as usual. But you notice that once you put the octet on both sides, you're going to have no valence electrons left to put on the center atom. And there's only 2 bonds, which make 4 electrons. So beryllium doesn't have a full octet. However, it's one of the elements in the periodic table that is able to violate the octet because of the low number of electrons. So it's going to be an octet violator, and there's 2 domains, 1 bond and 2 bonds, which make it linear, both molecular and domain geometry. Electronegativities, beryllium is 1.5 and chloride is 3.0, so the bond dipoles are going to point towards the highest electronegativity. So it's going to point outwards towards the chlorides, giving both chlorides partial negative charge and beryllium a partial positive charge. Since chloride is going, the electron is going to drift towards chloride. And because of the two domains, and because they're both the same, there's going to be no net dipole. Both bond dipoles are going to cancel. And because all domains are the same, it makes it nonpolar. Next, we have carbon tetrachloride, which is going to have a Lewis structure that looks like this. The electronegativities of carbon is 2.5, and the electronegativity of chloride is 3.0. Therefore, since chloride has the highest electronegativity, the bond dipoles are going to go outwards towards the chloride, giving the chlorides partial negative charges because they're going to be receiving an electron, and the carbon is going to have a partial positive charge. Now, there's 4 domains, 1, 2, 3, 4, which is going to make it tetrahedral in both the domain geometry and also the molecular geometry. So it's going to look like this. And because all of the domains are the same, there's going to be no net dipole because all the dipoles will cancel, making it nonpolar. Lastly, we have ozone, which has a Lewis structure like this. But because oxygen is left without an octet, you're going to need to redraw it like this, with a double bond on one of the O's. The double bond can either be here or here. So the actual resonance structure is going to look like this, and it's going to have a shared bond, making 1.5 bonds between the O's. Now there's 3 domains, 2 bonds, and 1 non-binding pair. So it's going to have a bent molecular geometry. And there's no bond dipoles between the oxygens because they're the same, so therefore they have the same electronegativity. However, the non-bonding electrons cause a dipole to go down, and there's a net movement going down. And because there's a net movement, and not all the domains are the same, it's a polar molecule. Therefore, oxygen difluoride and ozone are going to be the polar molecules. So the answer is 2.
So some common mistakes may be drawing the wrong Lewis structure, maybe because you calculated the wrong number of valence electrons, or you didn't fill up the octet correctly, not considering resonance by having all the possible forms that you could place double bonds, counting double bonds as 2 domains. No matter how many bonds there are, it just counts as 1 as long as it's in the same area. Because oxygen uses all the same atoms and they all have the same electronegativity, there is no bond dipoles, so none should be drawn. It's a possible mistake to not count the non-bonding domains and only counting the bonds. And lastly, not drawing molecular geometry to see if the dipoles will cancel or not, because you can't do that just based off the Lewis structure.